Okay, can everybody see well? Alright. Do you remember anything from last time? Okay, we'll start over. So, like we said, the first step after logging in is what? It's TCSH, right? Okay. After TCSH, we actually go to the folder where we're working. What was the folder last time? Okay, let's create a new folder. CSCE 586 Spring 2013. Okay, here lab 1. Anyone remembers what the command is now? Okay, the command for everything you're gonna do in this course after TCSH is cat setup 45. Okay, have to remember that. After you perform this command, you can do anything with the VLSI software that we have. To start Cadence, you type the command virtuoso and you follow it by an ampersand. Okay, let's hope it works. Okay, and this is Cadence. Now, as I've said before, Cadence is much easier than Magic. There are no commands, everything is buttons and menus, and you have feedback on everything you do. So once you start Cadence, you're gonna see these three windows. Okay, the what's new window is just what's going on in this version of the software, and you don't need it, so you close it. You're left with these two windows, the library manager and the main window. Now the library manager, you can open it later. Let's look at the main window. This is where everything's gonna happen here. Now what you see here is a log. Every error you have, every warning you have is gonna be displayed here. So whenever something's not working in your circuit, you look at this window here and you see what kind of errors you have. So this will give you feedback about every error or warning that you have. Here you can actually write commands. There are complex syntax of commands for Cadence. There's a language just for Cadence, programming language. But we're not going to go into that because you don't need it. So aside from the command line here and the log, here you'll find the menu entries where you can launch the library manager and some other stuff. But basically you're only going to need to launch the library manager from here. So first step is to launch the library manager from this window. So it's tools, library manager. When you open the library manager, you're going to see the available libraries. Now these libraries are, first of all, let me explain what a library is. A library is basically a collection of gates or devices or anything that a company supplies to you. Now in Magic, you saw that there were no libraries. When you did your project, you created your own library. You created your own gates. But in professional environments, you don't create your own gates. You go to a company and you say to the company, I want to buy a 45 nanometer library. And the company sells you their library, and the library includes everything you might think of. multiplexers, adders, multipliers, all kinds of gates, all kinds of flip-flops. So that's what you have in commercial libraries. Now these are not commercial libraries, these are educational libraries. So you're not going to find everything you want, but you're going to find the basic things. So in this library here, and by the way, it's all 45 nanometer here. So that's what we'll be working on. In this library, you're going to find NMOS and PMOS devices. Now, does anyone know what the difference between NMOS, VTL, and VTH is? VTL, VTH, what does that remind you of? Yes, exactly. So NMOS, VTL is an NMOS transistor with a low threshold. VTH is for a high threshold. VTG, I'm not sure, but I think it's for general case. So which one you think we would prefer here? Low threshold. That's right. We actually prefer the low threshold. Why? Anybody knows why? Power? Yeah. Speed. Yeah. Speed is the main concern. Yeah. Basically, if you look at the ID equation, once the threshold is lower, the ID is bigger. So actually this will give you faster transistors with VTL. Now the power will actually increase with VTL. So you're increasing the power, but it's actually a faster transistor. So everything we do is going to be VTL. Okay?
But it will be more sensitive to noise, like acoustic element.
Yeah, exactly. Yeah, that's one of the problems, that if the threshold is lower, then it's going to be more susceptible to noise. Yeah. Okay. So this is what you have here. And when you look at each cell has a number of views, but what you're going to use here is a symbol view. The symbol view is what you're going to place in your schematic. We're going to do that later. The other library here is for layouts. So we're not going to deal with it today. Once we go into the layout drawing in Cadence, we're going to look at this library. You can see there's metal 2 to metal 1, via metal 3 to metal 2. There's a contact. There's a bunch of built-in layouts. There's a layout for an NMOS and so forth. These libraries here, this library you don't mind it. We're not going to use it. This library is a generic library in Cadence. It has nothing that is technology specific. That's why the only things we're going to use from this are VDD and ground from analog library. So the only things from analog library we're going to use are VDD and ground. Basic library, it's also a built-in library in Cadence. We're not going to use anything from here, neither from here. So we're left with the last library here. This library has the gates. For instance, here there's an AND 2 inputs and 2 inputs times 2. Anybody has any clue what AND 2 times 2 means? This is a tricky one. What? Yeah, exactly. AND 2 times 2 means all the transistors have doubled the sizes of the AND 2 times 1. So if you have a very big load that you're driving with a gate, you use AND 2 times 2 because it has larger transistors than AND 2 times 1. So this is AND OR. This is a special gate. Mostly not going to use that, but you get the point. There's a full adder cell here. There's a D flip-flop. There's a buffer. There's a latch. The inverter is here. Basically everything. OR gates, OR, yeah, the OR here is 2 inputs. If you look at the NOR, you have one NOR that's 2 inputs, another that's 3 inputs. This is a very, very limited library. It's a educational research library. If I show you a commercial library, it has, for each gate, it has 30 cells maybe. There's like 2 input, 3 input, 4 input. And for each of these, it has multiple transistor width. So this is a very small library compared to actual commercial libraries. But it's enough for our purpose here. Okay. So say you want to make your circuit. Say we're gonna build just a random circuit that performs some function. You cannot add to any of these libraries. The first thing you do is you create a new library where you put your circuit in. So the first thing you do is File, New, Library. Let's call it my lib1. Okay. Now once you create a library, it's gonna ask you what technology you want to use for this library. So here you actually tell it to attach to an existing technology library, and then it's gonna ask you which technology library, and you select the first one here, NCSU, North Carolina State University. That's the university that actually built this library. And you select OK, and now you have this library here. Of course it's empty, there are no cells. We have to add cells to it. So the next step is to create a cell in this library. So we do File, New, Cell View. Okay. And in this window here, it asks us which library we want to put the cell in. It's my lib1. Which cell? What do you want to name your cell? Let's see. What should we make? Let's build a multiplexer. Actually, let's just build an AND. AND OR. Let's call this AND OR. My AND OR. Okay. And here, this is important here. What kind of cell do you want? Do you want a layout or a schematic? What we're gonna do today is schematic, right? So type, and we select schematic. Not schematic symbol, but schematic. And you leave everything as is. Press OK. Now a window should open where you can create your schematic. This is the window that appears. This is where you build your schematic. Okay. Now you can, if you want to, you can use shortcuts on the keyboard, which is the way that I recommend. It's much faster. Or you can use buttons on the toolbars, or you can use entries from the menus here. It all does the same thing. It's just different ways of doing it. So first of all, let's create an AND gate. Okay. So let me get the PMOS first. So I can, whenever you need a device or any kind of cell, you have to create an instance. You have to remember this name, instance. So you do create instance, and then you click on browse here. And from here you go to the library you want, and you select your cell, which is your instance. So what do I need here? I need a PMOS, right? So where do I go? I go to the devices library, and I select a PMOS VTL. Okay. And here, it's the last step, I have to select symbol. And then you would see this window that shows up here. This would list the properties of the transistor. The width is 90. we can change the widths, of course. The length, now I said the library is 45 nanometer, right? So theoretically here it's supposed to be 45. But they put 50 nanometer value. I'm not exactly sure why they put 50. It's supposed to be 45. But I just leave it 50 like that. There must be a reason for it.
What is the minimum size we can use it here? For example, we can use 22 nanometer.
No, the length you cannot change. You have to leave it. If you want to change anything, you would change the width.
Okay, wait, so we can use 22 for example.
No, what is displayed here is the minimum value of the width. Yeah. So if you want, you would increase it to as much as you want, but this 90 is the minimum. Yeah. Okay. So here, once you click on symbol, the PMOS here is displayed. You can place it wherever you want. If you want to rotate it, you can click on rotate sideways, or you can just manipulate it whichever way you want. So for the AND gate, I have two PMOS in parallel, right? So do sideways, and I place another PMOS. Okay. Now I need an NMOS. And these are my NMOS transistors. Okay. Once I'm done, I press on escape. Whenever you're done with something, you should always escape. Okay. Now I put some wires here. You click on wire. Create narrow wire is what you need to connect things together. I'm sure you've used a software similar to this before, like Multisim or PSpice or something. The difference, of course, is that this is a professional grade VLSI software. This software sells for hundreds of thousands of dollars. Very expensive stuff. Okay. One thing I missed is actually the VDD and ground. So I go to instances again. Go to browse. And remember, I said for VDD and ground we go to analog library. Now here you search for VDD and you get the VDD, you place it here, and then you search for GND, you get the ground, you place it here. And now let's finish up the wiring. And by the way, you should always keep your eye on the lower left corner on the screen here. You can see it says point at location for the instance. This tells you what command you are inside now. If I want to exit this command, I press on escape. Now this space is empty, so you should always look at this space to know what mode you are in. So to create a wire, I can just click on W. It's the same thing as pressing here. So click on W, create your wires. And of course, we should never forget the body connections.
One question: if we keep the body unconnected, what is the default connection?
It will tell you there's an error in your circuit. So let's try it now. Let's try to save. What's that? Yeah, I did it on purpose. I just want to see what it says. If you look at the toolbar here, there's this button which says save, and there's this button which says check and save. So this will check your circuit and then save. So let's try this button. It tells you there were 0 errors and 1 warning. So you go back to the log window, the main window. You see what the warning is, and it says here warning. I lost it. Warning, pin B on instance M1 floating input output. So this is instance M1, pin body is floating, so it tells you that. If you don't connect it, the circuit is not guaranteed to work, because body is essential for the circuit to work. Most of the time, if you don't connect the body, it might still work, but to be safe, you always connect the bodies. And by the way, there's something very annoying about Cadence. I don't know if they did it on purpose or what, but if I try to connect this on this dot, if I try to connect it here, it will display an error. It doesn't like wires connected, like 4 wires on one dot. You can at most connect 3 wires to one dot. So if I have to connect it, let me delete it. Okay, so if I need to connect this to VDD, I cannot connect it here on the dot. I have to connect it here. Okay, it's just one of the things Cadence complains about. Okay, now I was thinking of building an AND followed by an OR gate, so let's do that. And instead of placing new instances, I'm gonna try to copy some of the transistors here. So let's zoom out, and by the way, you can zoom out by pressing Control and scrolling on the mouse, so you can easily zoom in and out like that. Okay, now to copy something, you go to edit, copy, or you can just click on C. So if I click on C, if you look at the lower left corner, it says point at object to copy. So this is how you know it's actually working. So I click on this transistor, and then I click here, and then I do it again. Wait, I'm actually making an OR gate here. So, well, I still need an inverter here. Let's try to move something. So move, just click on move, and then you click on this. And by the way, there's one tricky thing that I needed to tell you. If you want to flip something sideways, there's no command to do it. It's actually something very hidden. You have to click on rotate, and then press on F3. I don't know why it's so complicated. You press on F3, and then you click on sideways, and then you click on this. It's very inconvenient. I have no idea why they did it this way, but it's just something to keep in mind. So this is not an optimal circuit. I'm sure you can simplify the Boolean algebra so that you can at least eliminate this inverter here, but we're not looking into that now. So what I'm doing here is A and B or C, okay? So I need to actually copy this whole inverter and oh, okay, so copy it, put it here, and then connect it like that. Okay. Now there's still one thing that I've actually missed. Anybody knows what it is?
You have to take a input is wrong.
What's that? Yeah, all the inputs and outs are floating now, but other than this issue, there's one thing that concerns the sizing. No, this doesn't matter here because this is not a layout. This is just a.
The PMOS in the first step is writing too much component.
No. Hold on a second. Oh, there's an error here. Ugh. Yeah. By the way, to delete something, you click on delete and then you click on the thing you want to delete. I'm supposed to connect the output here. I was connecting the input. But still, there's something that I've missed. It's an optimization thing. It's not a. Remember sizing of the transistors? Here you have two NMOS in series, so they're supposed to have double the width, right? So to edit the property of something, you press on Q, or you can just go on to edit properties object, which is the same thing. So I prefer on just pressing Q, and I go here and I change this width to 180. Then I click on what's that? Double or half? Where in this gate you have to double the sizes of the NMOS. No, that's the width. The width originally is 90, so we double it to 180.
So in previous design, we used kind of a smaller NMOS, but the size of PMOS is twice as large as NMOS.
Right. Yes. Okay. Okay. You're right about this. So before sizing any of the gates, let's deal with the inverters. So for the inverter, you're absolutely right. This should be double the size of the NMOS. So it should be 180. Okay. The same for here. Because as we know, PMOS is always should be double the size of the NMOS, right? Except for, okay, let's look at this case. In this case, I have two PMOS in series. Remember the sizing problem we used to do 585? When we have two PMOS in series, it's not enough to have double the size of the NMOS. In this case, let's see the effective resistance. So here it's 90. No, it does. Of course it does. It matters a lot.
It's racialized
It's
or not?
ratioless in that the value will always reach either VDD or ground, but it won't be symmetric unless the sizing is correct. It's ratioless because it always reach VDD or ground, always, but it will not reach them at the same speed.
But as long as we know the mobility of the PMOS is twice of the NMOS, we just make the PMOS part to be twice large as the NMOS.
Yeah, that's what we did in the inverter, right? But in this case, the pull-up, remember the propagation time? RC, 0.69 RC? So this is equalizing the rise time and the fall time propagation. So we have to equalize them. In order to equalize them, let's make this one 180. It's actually, in this case, it's either 4 or 8 times the size of the NMOS. I don't remember, but let's use 4 times.
Resistance of field should be 4 times.
Yeah. So let's make it 4 times, which is 36. 360. Apply. Then select this one. Make it 360. Okay. If you look closely, you can see L and W. Can you see them on the screen? Yeah. And going back to this gate here, it's the same problem. Over here we have 2 NMOS in series. So I guess in this gate, we can either, we don't have to do it. We can make the transistor double the width, but it's not necessary. If you have doubts, by the way, you can look at their built-in libraries and see how they size their own gates. So let me look at their own AND gate and see what they actually did. And schematic. Yes. Here it tells me that you cannot modify this file because it's built in, so I tell it okay. And by the way, their schematics are very, very hard to read. I have no idea how they do it. But I'm assuming this is the inverter here for the output, so these must be the NMOS and PMOS. So they have 500 for the NMOS. And 500 for the PMOS. So yeah, that's what I was thinking, that for the AND gate we leave them basically the same width. Okay, so we're almost ready. What do we still have to do? Inputs, outputs, right? For these, we use something called pins. So we have to place pins. To place a pin, you can either press on P on the keyboard or click on create a pin here. You won't get lost. There are 3 ways to do things. Let's call the first one A and select input, and then you click here and then write B, and I still have C. For C, let me create a wire first. Okay, there's one more thing I wanted to demonstrate. It's that in Cadence you don't really have to connect things physically for them to be connected. So if I didn't want to make a connection here to C because it looks ugly and would complicate things. I can just label this wire as C. If I label this as C, they will be as if they are connected. It will make your circuit look nicer, cleaner. So I click on create a wire name here, and I write C, and I click here, and now C is connected like that. And finally I place an output pin, so I change this to output. Let's call it out, and I place it here like that, and I'm done. So I click on check and save. No errors, no warnings, it's all good. Okay, I'm ready to simulate the circuit. Okay, so any questions so far? Okay, so let's go into simulation. For simulation, we're going to use something called ADEL, Analog Design Environment Light. So we go to ADE, and now this is where we're going to set up the whole simulation. So instead of writing SPICE commands, we're actually going to configure them graphically. So if you prefer, by the way, to still write SPICE commands, you can do that and load the file here. It's the same thing. But let's do it the graphical way. The first thing is to set up the simulator. And here you have to always change spectr to HSpice, because this particular library is designed to work with HSpice and not spectr. Spectr is a simulator very, very similar to SPICE. It's supplied by Cadence as a built-in simulator. It works very similarly to SPICE. It's very good. But here we're going to use HSpice D. So that's the first step. We change the simulator. And it's taking a while. Well, that's not normal. I hope the license hasn't expired. Okay, I'm gonna kill the program and then launch it again. Okay, so I actually killed Cadence and I'm gonna launch it again. There was something fishy going on. By the way, today we'll finish everything that has to do with schematics. So we'll have a long time before the next lab session, which probably will have a long time until you do the homework, and then we'll go into layout. Also, layout should only take one session, and then once we're done with that, we'll go into Verilog and synthesizing. So it should be pretty quick. I mean, unless we keep having software problems like this. Anyways, so by the way, if you want to open your previous cell, of course you have to always open Cadence from the same folder that you working on the project. If you open Cadence from a different folder, you can't access your circuits. You have to be the same folder. It's the same folder. You also should type cat setup 45 in. So let's open our schematic. Well, it actually locked my file because I force closed it, which sucks, but let's do it. And then launch ADE. And then, like we said, we should change the simulator, the first step. This is where the error occurred first. Maybe it's because my directory is full, so this is where it's gonna store its simulation files. The simulation files are probably things that you don't need, like waveforms and things that are temporary. So you can just place them in temp to save space in your account. So let's try that. Hopefully it will work this time. Maybe not. Okay, looks like it worked. So now we've changed our simulator to HSpice. You can see it here. Now what you usually do is you go through all these menus and set up all the simulation stuff you need. Not everything, but most of these we're gonna go through. So second thing is to set up the model So second thing is setup, model libraries. These are the transistor models. Remember in Magic we supply the transistor model file, TCMC18. This is the model of the transistors. It's the same thing here. We have to give it model files for the transistor. So you click on browse here, and then here you have to go into HSpice models. It should be displayed right away in the project directory. And here you select either HSpice nominal or fast or slow. Do you know what fast, slow, nominal mean? Okay, nominal means, you know, when you fabricate a chip, some transistors turn out to be faster than others. You can't control that. There are some random things that happen during fabrication. Nominal means all the transistors operate normally. Fast means during fabrication, some of the transistors, the transistors happen to be faster than normal. So this is what fast means. Slow means transistors are all slower than usual. So what you need most of the time is nominal. Okay, I lost connection again. Well, this is exciting. Oh, okay. So it's working again. So, like I said, if you want to test your circuit in the worst case, slowest case, you select SS, right? Okay. Now, in more advanced libraries, they have SFFS, slow, fast, slow. Means that the NMOS is slow, the PMOS is fast, or the PMOS is slow, NMOS is fast. Okay. So once I get that, that's all I need here. I click on OK. And then you can set up the temperature. I usually leave it at 25, which is room temperature. You can change that. Stimuli is very important. This is where you select the waveform of your inputs, right? So we go into stimuli. Here, for each of these, you have to enable it and then change the function to either pulse or whichever, but usually we use pulse for testing. And for the VDD here, it's going to be 1.1. For this technology, the VDD is 1.1. So voltage 1 is 0, voltage 2 is 1.1. The period, let's say for the first signal it's going to be 0.5 nanosecond, 0 delay time. Rise time, let's make it 30 picoseconds. Same with the full time. Pulse width 0.25 nanoseconds. Okay, and then don't forget to click on apply before moving to the next one, because it's going to forget all these values. So you click on apply, then you move to the next one, and you do the same thing over again. So 1.1, and here we double the period, 1 nanosecond, 0. Okay, and finally here we also double the period to 2 nanoseconds. Okay, so we're done with the inputs. But remember, we have VDD. We still have to set VDD. We haven't set it yet. That's where we go. That's when we go to the global sources. So we have inputs and global sources. We move on to the global sources. we have VDD ground, we enable it, and it's DC, right? It's not a pulse. So we leave it as DC and we put 1.1. Apply, okay. So we're done with the stimuli. Simulation files, if you have some SPICE files, you can load them, but you don't need to. Next step is analysis. Now what do we usually do here? Remember? Transient, right? So we select on tran. Start 0, stop 2 nanoseconds. Step is for the accuracy of the measurement. 5 pico. If the circuit is too big, 5 pico will make the simulation slow, so you can choose a high, larger value, but 5 pico is good accuracy. Let's make it 10 pico. And you make sure that it's enabled here. Okay. So we're done with analysis. Variables, we don't have any variables, but you could actually specify a variable. For instance, you can go into one of your transistors and in this field of the width write variable name, and then here you can add a variable and you can change it and see how it happens in the simulation. We're not going to do that now. And then you go to the outputs, which are going to be the outputs of the plot, the simulation plot. And you don't actually go into setup. You go into to be plotted, and you select this option, select on schematic. And here you click on each signal that you want to track. So if you look at the lower left corner here, it says modify plot. So that's how you know what you're doing. So I click on A, I click on B, C, and outs. You can see all of them are now here on their outputs. And we're basically done now. We can run the simulation. But suppose you wanna you have something to do, so you close Cadence and then you come back later. Instead of doing all this work again, you can actually save your simulation state so that you don't have to do all this work again. So you go into session, save state, and you save it here. You name it whatever you want. So save it my state. Do okay. Then the next time you can just go into session, load state, you can load it. You might have to change the simulator to HSpice before you load the session. I don't remember, but check that before you do it. So to run the simulation, you can just click on the green button here, which says netlist and run. And it will show you the plot. Now in order to separate the plot, you can click on this button on the toolbar here. We'll separate them. You can see A, B, C, and out. So this function is supposed to be A and B, and all of it, or C. So I'm not sure if it's...
Can we change the font of the curve?
The colors, you mean?
The font.
The font?
Not the font of the curve. The font.
The font of the curve.
To be more clear.
I can probably...
It's dotted, right?
What's that?
Dotted line. Dotted curve.
Yeah, you want it like to be bold or something. There's a way to invert the... I mean, it's clear here for me. For you, it might not be clear. Large. Extra large. No, this is just changing the font. There's a way to to actually invert the colors. Color scheme, black. Is this better? No. Maybe gray is better. Okay, let's just get back to white. Okay. So let's just check that. So whenever we have C, we're supposed to have 1. That's correct. Whenever C is 0, it's an AND function between A and B. So it's correct. Is everybody satisfied with the results? Okay. That's good. So this is everything for today, I guess. We did a circuit and we did a simulation. There were more things. Yes.
Is there any convenient way to assign a value to a bus?
To a bus.
To input with multiple bits?
Yeah. No, not that I know of. Because here in the stimuli, you can only set it for one signal at a time. No, I don't know of any way. For that, you would need a more advanced simulator. Something like a mixed signal simulator or nanosim or something. Yeah. I still wanted to talk to you about how we can create a symbol out of this, so you can use it as a block in other circuits. Also, how to measure power, static power and dynamic power. But I think we can do that maybe next week. Next week would be fine. And then we can go to the lab and try it out if you want. Because today we don't have any time left. Okay then. We'll see you next week.